You're welcome to the White Academy. So, specifically this moment, so we'll be looking at an aspect that is called adsorption isotherm. Adsorption isotherm. This a very, very important aspect in catalysis. Specifically, it has to do with surface catalysis. So a process whereby molecules interact with the surface. Now, let's look at the word adsorption. I want you to differentiate this one from absorption. When talking about absorption, it has to do with the whole molecule, entering a particular bulky medium, probably maybe liquid or solid as the case may be. So that particular molecule is absorbed in. But when you talk about adsorption, actually this one is a surface phenomenon. Okay, so it's actually an intrinsic property of any surface. All right, just like you can look at it, this is a surface. All right, and then this, the ink or the imprint on the surface. All right, so if there's no molecular interaction between this white surface and then this ink here, all right, so you will probably not be able to see the writing as it were. So what we're saying is that molecules interact with surface, all right? So actually the concept of this now, once we have found out this, then we have applied it in heterogeneous catalysis. So a process whereby actually we can hasten the rate of chemical reaction. So if that is talking about adsorption, then what is adsorption isotherm? This has to do with the variation. It is the variation of the surface coverage, all right, with pressure at a given temperature. So we want to note that. So that's a variation of the surface coverage, all right? So when you talk about surface coverage, we are looking about at that particular portion of the surface that actually where the adsorbate, stick to, all right? So, and that also is a measure of the amount of, molecule that is adsorbed on that surface. So, when you talk about this, the extent of adsorption all right, is usually expressed in form of the fractional coverage. So when I say fractional coverage, invariably I'm still talking about the surface coverage. But then we want to look at experimentally determine, the extent of adsorption on a specific surface. All right. So let's denote, let it, be the surface coverage or the fractional coverage, all right, that we are interested in. So this surface coverage actually is defined in terms of the number of adsorption sites, occupied divided by the number of adsorption sites, all right, unoccupied. All right, so it should be noted. So the number of absorption sites that is occupied by the adsorbate, divided by the number of adsorption site that is unoccupied. So this is how we express our fractional coverage, or what we call the surface coverage. All right. Most often than not, we express this surface coverage or fractional coverage, as the ratio of the volume, where V represents the volume of the adsorbate, divided by the V infinity. All right. So where V equals to the volume of the adsorbate, all right, and V infinity, that is equivalent to the volume, all right, of the adsorbate, all right, for a complete, coverage of a monolayer. Monolayer. In other words, we are relating the volume of the adsorbate, okay, with the volume, assuming that the adsorbate, molecule, have totally covered the surface, but mind you, with respect to what? A monolayer coverage. So this is how we express this. Now, why are we interested in this? Okay. So most often than not, actually want to determine the rate of adsorption on our sample. When I say sample, we're talking about substrates. Now, I have the understanding that, like I said, this is an aspect of what? Catalysis. Okay. So, and then when we talk about catalyst, we are talking about anything, that easing up, the rate of chemical reaction. Also, it can also reduce the rate of chemical reaction as the case may be. All right. So, but then we want to look at, the affinity, okay, of the adsorbate, on the sample or the substrate. Is that okay? So in order to measure the effectiveness, of the sample or the substrate as the case may be. So that is what we're looking at. So now, we need to understand a bit on this principle called adsorption, because actually this is an integral part of this study. Now, when you say, I've earlier said that the interaction or the attraction, of a surface, for molecules, all right, maybe be it gas or liquid as the case may be, so the affinity, the attraction is what we term the what? The adsorption. So I've said that earlier. But then there are two major ways by which molecule can actually interact with surface, all right? So it can be via or physical means or physical process. So in that sense, when you talk about adsorption, all right, so we can look at it, physically in terms of physisorption. All right, physisorption is talking about physical adsorption. All right, so take note of that. Then we can also talk about chemisorption. Chemisorption, so of course, that's talking about chemical adsorption. All right, so these are two different ways by which a molecule, when I talk about particles, molecule atoms can interact with the surface. So, but let's look at physisorption. What is this all about? Well, when you talk about physisorption, okay, usually the primary form of interaction has to do with van der Waals force of interaction. Van der Waals force, van der Waals interaction. All right. Now, from basic chemistry, you know what to call or what we term van der Waals. All right. So when you talk about van der Waals, actually is a weak kind of electrostatic interaction. Is that okay? So this may include, dispersion. That's what we term London dispersion. All right. So London dispersion force or dispersion interaction. All right. Or we can also talk about a dipole-dipole, form of interaction. Is that okay? So, but one thing about van der Waals force is that what? It is short-lived. And then it has a long range of interaction. So it has a long range, of interaction. between the species that are involved, in it. So I've mentioned one thing. So looking at the nature of this, of course, just to recall a bit. Remember when you talk about iodine crystal, okay, one of the property of iodine that it sublimes easily. So why does it sublime easily? You can imagine it's solid, okay? So it's because the intermolecular force there actually is a form of van der Waals force, which actually can easily be cleaved and can easily be broken. So that is one characteristic of its assumption. Is that okay? So it has a long range form of interaction which has to do with what van der Waals force of interaction, so which could be dispersion or dipole form of interaction. What we're just saying in essence is that when a molecule is interacting with the surface via phase assumption, okay, the effect, is short-lived, such that it is easier, the molecule has a tendency, or the atom has a tendency of what? Of breaking loose, easily at the slightest, perturbation, probably as a lot of temperature or pressure as the case may be. So that is what viscoption is all about. Then another thing about viscoption is that, when you talk about catalysis, actually we want to, create a new bond, by breaking the initial bond and then forming the new one. But what you find out is that most often when molecules interact via viscoption, is that okay? They usually retain their identity. The identity of the molecule is retained. Okay? So that is the only little thing that can just happen, maybe just a kind of slight distortion. Is that okay? But you can't have molecular fragment on the surface like in the case of chemisoption, as we soon found out. So what brings about that? It's so very simple that the bond dissociation energy, or the entropy of dissociation of adsorption, related to viscoption actually is of the magnitude of about 20 kilojoules per mole. Actually, this is not sufficient enough actually to cleave any bond. Is that okay? So that's why most often than not, actually the molecule via viscoption actually still retain its identity. So please take note of that, okay, that a molecule can interact with a surface via what? Via viscoption. Then what about chemisoption? Yes, as the word implies, chemical interaction. And of course, understand that chemical interaction actually has a stronger effect. And the one particular thing, actually, there's a close proximity, between the adsorption site, and the molecules or atom involved. So close proximity, all right, that is, they are held together strongly, usually via covalent bond. So that is what happens there. So close proximity, all right, so, or interaction. Is that okay? Between the molecule, okay, or atoms, okay, and the adsorption site. Is that okay? So, but then, you see, it's a very interesting chemistry such that, when molecules interact with the surface via chemisoption, okay, one particular thing you must also notice that the surface is not uniform, right? The adsorption site are scattered all over. So if that is the case, when when a molecule begins to interact with the surface, based on the principle that every system wants to attain the minimum energy possible. So when that molecule comes, those atoms are looking, for the maximum coordination site. Please take note of that. So the molecules are looking for what? Maximum coordination site. So what is the consequence of this? So when a molecule, let's take for instance, now this is a surface, all right? So take note of that. So on this surface, HCl, let's say hydrogen chloride vapor, is interacting with this surface, all right? So when this molecule comes here, this is surface, all right? Each of these atoms, they have different degree of affinity, for the adsorption site. While hydrogen is looking for, the maximum coordination site for itself, chloride, chloride atom or ion also is looking for what? For the maximum coordination site for itself. So the implication is that there is a stress on this initial bond, all right? So why this one, is looking, get itself fixed somewhere here. This one is also doing what? Getting itself fixed somewhere here. Then what happened is that this bond, will be broken. And so when that happens, okay, that is the principle of what? Of a surface catalysis. Is that okay? So because molecules are looking for what? For the maximum adsorption site, then that one actually put a stress on the initial bond so that there's a cleavage, and then molecular fragments are formed. All right. So this is the basis of what? Of surface catalysis that we're looking at. It's a very interest of we have found out that organometallic complexes, and then basically metals have been found useful, in catalysis. So tremendous. We have seen palladium, platinum, nickel, being used in hydrogenation. Okay, so and so many other catalytic process and so forth. So this is the basic principle. This is the basic principle. Even though we'll not begin to look at, okay, which one is homogeneous, which one is heterogeneous. So subsequent video we might begin to look at the differences and then the advantages of one over the other. So but this is a principle, and that is our point of focus. Don't forget adsorption isotherm. Like I've said, that has to do with variation of the surface coverage with pressure at a given temperature. Let me also quickly note that don't forget this temperature. Anyway, you'll soon find out. I'll begin to look at the kinetics, of this process. So we'll soon find out. So I hope this one is understood. So let me give you, for instance, what is that? Another thing is that, in the course of interaction, okay, molecule may be disorderly or orderly oriented as the case may be. All right, because we found out that for CO on palladium, is that okay? So when CO actually is adsorbed on palladium, actually there's some form of repulsion, in between the molecule, the CO molecule, all right? So the reverse is the case, for interaction of oxygen with tungsten. Is that okay? So whereby actually there's a kind of attraction, okay? So why this one actually interact via repulsion on the surface of the palladium, this one actually is just fine. So all of this actually can result in a kind of, orderly or disorderly distortion or arrangement of adsorbate on the surface, So note that. So actually there's no perfect surface, so you don't expect that actually all the adsorption sites will be uniform all through. Thereby there will be variance, in the concentration at different region on the surface. So now, so good as it is, so we are so interested in the mathematical application of this, which also have found its industrial usefulness. So we're going to be looking at different kinds of adsorption isotherm, and then we'll see how this can be used. We're looking at various form of adsorption isotherms that are of interest, and then of industrial application. So one of those include the Freundlich, Freundlich isotherm. All right, okay. So the Freundlich isotherm. We also have the Temkin isotherm. All right. We also have what's it called? So we have Langmuir isotherm. All right, and then we also have what we call Betz isotherm. All right. So don't forget now when you want to study adsorption isotherm, okay, usually one of the conditions is that the adsorption rate, and the desorption rate must be at equilibrium. All right, so that's one of the things. And then for the fact that the surface coverage also vary with the vapor pressure, of the gas. So adsorbate as the case maybe. So take note of that. So most of what we're dealing with here actually has to do with adsorption equilibrium. So we want to make some derivatives. Is that okay? So we have this, this actually, let's begin with this. All right. So then we look at bet isotherm and so on and so forth. So now let's look at Langmuir isotherm. Now, looking at Langmuir isotherm, how do we derive that? Okay, let me quickly say this. So for Langmuir isotherm, you have that, what is it called? Your surface coverage, okay, is equal to BP, 1 over. So you will soon find out how we derive all of this. So where theta represents your surface coverage. And then in terms of a bet isotherm, okay, theta, is equal to V, over V monolayer, and that is equivalent to your CZ, okay, then into bracket 1 mono minus Z, then open bracket into bracket, what is it called? 1 minus, 1 minus, C. So this is what you have. So that is about bet isotherm. Is that okay? So for friend Luis, okay, C1 is written in form of what is it called? That is your equilibrium constant Kp, then 1 over C2. Is that okay? So and then for the other one, so your C for Temkin, so C1 actually is written in terms of Kp, lane C. So as the case may be. Now these are various adsorption isotherms that you can have. But then for today, like I said, I'm particularly interested, excuse me, so theta, so C1, so C1, so as the case may be. So that's what we have. Now, this is C2, so take note of that. So like I said, theta represents your surface coverage, so as you have. So now, I'm particularly interested in this, okay? So in looking at this, what I want to simply do is that we want to derive it, both kinetically, and thermodynamically. So, and then I want to see actually we obtain this, okay? We will not worry much about these two, okay? Because these two actually, they are a way of taking care of some of the adsorption that Langmuir has made, which actually has resulted into a kind of deviation from the isotherm that we're dealing with. Is that okay? So bet isotherm, as we soon find out, has to do, with multilayer adsorption. So we'll soon find out. So just be anticipating that I'm going to derive this, I'm going to derive this. Is that okay? So there are several other isotherms, to be able to explain this relation, of surface coverage as a function of pressure, as the case may be. All right, so we'll move. So in that sense, it follows that when you have, let's take a monolayer absorption. Okay, before we move on, what are the Langmuir's, assumptions? What are the Langmuir assumptions? Because that one formed the basis for this derivation. All right. Number one, Langmuir, in a very simple way, illustrated that the surface, is uniform. That is, all adsorption sites, are what? Are equivalent. All right? Okay? So, Langmuir assumption, so it's telling you that all surface, are what? Are uniform. Okay? So, in other words, that what the concentration of the adsorbate, is the same anywhere on the surface. Okay? That's the first assumption he made. Okay? And then another assumption he made is that there is no intermolecular interaction. Is that okay? No intermolecular interaction. And then he also made mention that all adsorption, follow the same mechanism. Note all of this. And then he also mentioned that the, what's it called? Adsorption, okay, does not exceed, a monolayer. So these were the first assumptions that formed the basis of Langmuir derivation. Take note, number one, that the surface is uniform, that all of the dosages are equivalent, so no molecular, intermolecular interaction, so there's no interaction between the neighboring atoms or molecule. And then, again, all adsorption, follows the same mechanism, okay? So that all adsorption follows the same mechanism and adsorption does not exceed a monolayer. So if all of these are in place, then we can then look, at adsorption, of a single species, undissociated on a surface. So just take a look at this. So we can begin by this. All right. Now, look at that. So, given an hypothetical equation, A, plus S, reversibly, to give you A, dot S. So, this is an adduct. Is that okay? So, when your gaseous reactant, adsorbate react with the surface, then you have this adduct, formed. So, from the basic principle of equilibrium, like I've said, okay, we are considering this adsorption isotherm at what? Adsorption equilibrium. That is, the rate of adsorption, must be equal to the rate of desorption. So now let's go. So it follows that if this is R1 and this is R2, so this is the rate of forward reaction and this is the backward reaction. So, of course, you recall law of mass action, and then active masses. Is that okay? So, as regards to equilibrium, so when we want to express rate law. Now, look at this. So, it follows that R1, okay, is equal to the concentration of A. All right. Let's introduce A, okay. Let's just start with the proportionality constant. So, to give you this, of course, then you introduce your K1, which is your, the equilibrium constant for the forward reaction, okay? And then you have this, okay? So let's call this one equation 1, right? So I hope this is mathematically making sense. Then R2, which actually vary, as A, dot S. All right, so which is concentration of your adduct, when the molecule has adsorbed to the surface. We are talking about the surface occupied now. So therefore, R2 now is equal to K2, A dot S, as you can see. So then, at adsorption equilibrium, so this just indicate that this is at adsorption equilibrium, then it follows that R1 is equal to R2. So such that equation 1 is equal to equation 2. So then you can have that K1A, surface is equal to K2, A dot S. Is that okay? So of course, by manipulating this equation, you agree with me that you can have K1 over K2 to give you A dot S, okay? Then A, then S, as you can see. So if that is the case, can we find a definition for each of those terms? Is that okay? Because as regarding gas, actually, we shouldn't be talking of concentration. Actually, most often we talk about what? Gas has to do with pressure. Yes, but there's no trouble. You'll soon find out all of this. So we can write this K1 over K2, and give a kind of overall equilibrium for the process. So let's call that one big K. Is that okay? So it follows that K now is equal to A, dot S, all right? All over, what is it called? Yes. So you have this. Good. So now let's quickly define all of these terms. So when you say A dot S now is equal to theta, which is our surface coverage or the adsorption site occupied. Okay, so adsorption site, occupied. All right, so that's surface coverage or your fractional coverage as I've introduced earlier. So surface coverage. So take note of that, very important. So just follow carefully. Then, taking the second one now, this actually your gas. And like I've mentioned, actually, it will be most appropriate for us to express this one, in terms of pressure because we are dealing with gas. So in that sense, now, when it comes to kinetics, actually, it's easier, to study, even especially generally when it comes to practice like kinetics or, kinetic theory. So actually, we have chosen gas, as a state of interest, of course, because you know that those molecules are far apart. So it's easier for you to deal with a single molecule, than in a bulky state, maybe like in liquid or where those forces of interaction are much more intense. So take note of that. So therefore, if this is a concentration, I say let that one equals to the pressure. Okay, so that's the pressure or the vapor pressure, you know, uh, of the gas. So take note of that. And then we define S, as our vacant site. Now, of course, if the whole surface is unity, is one, okay, and then theta here is the what? Is the fraction of the surface that is occupied, then you agree with me that the only space that we have left as vacant can be expressed in terms of 1 minus theta. So this is very, very simple. So therefore, we can go on and introduce all of these things, into our equation. So let's call this one equation 3. So then we have K now is equal to theta, all over P, into bracket 1 minus theta. Is that okay? So let's call this one equation 4. All right. So now, you can permit me to say that let K, equals B. All right. So my B here actually is the same thing as my rate constant. So if that is the case, it follows that I have B now is equal to theta, all over what? P into bracket 1 minus theta. Now note, every derivation I'm doing here actually is basically from thermodynamic point of view. Is that now thermodynamic, derivation. So it will also be very good that also we derive it what? Kinetically. So and I'm going to make, elaboration on what by kinetics, what by thermodynamics. So take note of that. So, but then, like I've told you earlier, that each of these isotherms are expressed, in what? Are expressed in their fractional coverage. Is that okay? As a function of the pressure involved. So if that is making sense, I want to make theta, my subject of the formula. All right. Now look at that. So from equation 4, all right, it follows that BP minus 1, at 1 minus theta is equal to theta, right? So this was just simply mathematics. But then we are so much interested in the significance. So we move. So in that sense, BP now is equal to theta, plus BP theta. So making your theta the sort of formula, you have this, and so therefore your surface coverage now equals to BP divided by 1 plus BP. So here is your what? Is your Langmuir isotherm expression. Is that okay? So with respect to the what? To the thermodynamic derivation. So take note of this. So where theta is the surface coverage, B is the rate constant, P is the pressure, and this is what we have. So very sooner or later, we're going to bring up questions, and then we can see actually this can make sense. So in practical application. So now, let's go to the second aspect, which is what? Kinetic derivation. All right? When we talk about thermodynamics, It has to do with, a lot of conservation of energy. Is that okay? All right. So how energy actually flow within a system. So that is what thermodynamics is all about. Okay. And then thermodynamically, a particular reaction can be feasible or not feasible. Okay. So that's very first thing actually that we consider. Is that okay? So if I will talk about thermodynamics before we now begin to talk about kinetics. Is that okay? Kinetics is simply talking about the rate at which your product is formed or the rate at which your reactant disappears. So all those things can help us to determine the mechanism, all those elementary steps that your reaction follows. So, but then let's look at this. So another thing I must also mention is this. When I started, I was looking at the extent of adsorption. Okay, how do we measure that? We can actually measure that by the rate of what? Of adsorption. Okay, that's talking about the theta, the t. Is that okay? So actually we can monitor, the progress of the reaction to look at how effective our sample or the substrate, is. Is that okay? All right. There are several techniques that have been developed. We can make use of flow techniques. Is that okay? Flash adsorption can be used. Is that okay? Even gravimetrical analysis. Okay. It's also applied here. Whereby you are using what's it called? Quartz. Crystal microbalance. So you can use that because that one is very sensitive for every minute change in mass. So this is a very interesting aspect. So, but then now let's move. So, like I said, so the rate of adsorption, is that okay? So can actually be used to determine, to monitor the reaction process, to know how effective that is. But let's move now. So that's what we'll be looking at. Is that okay? And then we can therefore say that your rate of adsorption, is that okay, is a function, all right, of the number of available sites. Is that okay? The vacant site. Is that okay? As well as the pressure of the gas. I come again. So the rate, of adsorption. Is that okay? So it's a function, okay, of the number of available sites, because there has to be available site before you can talk of adsorption. Then the vapor pressure of, the adsorbate you are dealing with, gas in this case. Is that okay? And then as well as the available or the vacant surface. So let's go. So therefore, we can say that the theta, the t is a function of what? N, all right? Then p, then 1 minus theta. Don't forget, I've defined all this time already. This is talking about your vacant site. So take note of that. That's the rate of what? Of adsorption. So take note of that. That's very, very important because actually we're going to look at 3 states of Langmuir isotherms. Is that okay? And then all these expressions are going to make sense by the time we get there. So let's look at this. So in this case now we can introduce our proportionality constant, of course, as usual. So it follows that the theta, the t is equal to k, all right? Then n, p, 1 minus theta. So take note of this. So let's call this one equation 5. Okay, let this one be your equation 5 and this one equation 6. So note that. So I actually want to use this kinetic derivation to justify the thermodynamic derivation and see how it goes. So from equation 6, so this is our rate of adsorption. So I've expressed that RAA, that is the rate of adsorption. Is that okay? Is equal to K, N Ka. So let's note that because that's for the forward reaction. So K subscript A or K sub A, then P, then 1 minus theta. All right. So can we also have rate of desorption? So that is R, dA. So that's the rate of, so R sub dA. So that's the rate of desorption. Okay. But the rate of desorption actually is independent of the pressure or concentration. So take note of that. It's only a function of the surface coverage. So note that, of fractional coverage. So therefore it follows that we have K, KD, all right? So is equal to N, theta. So, so as the case, so that's what we have. So now this equation 7. So, at adsorption equilibrium, as you know, RAA is equal to RDA. So therefore, it follows that KA and P1 minus theta, which is the surface vacant surface or vacant site, KD and theta. All right. So from here, so we can express this and say Ka over Kd. Is that okay? That is N. Is that okay? P, into 1, minus theta. Is that okay? So, and that is given as, that is Kd, that is N theta. So, and then, so let this, let K, all right, equals to Ka over what? Over Kd. Is that okay? So, like we said, so if that is the case, so it follows that this reduced to Kn P1 minus theta is equal to what? N theta. Are you getting my point? So, in that sense, now actually this can cancel out, as the case may be, because there are two common terms on both sides of the equation. So then we have Kp, 1 minus theta. Is that okay? So it's equal to theta. All right? So, but then you can permit me as well, in order for it to look so equivalent, that B, let B, equals to K. So anywhere I see B, what do I put? I put K. So in that sense now, it follows I have BP, 1 minus theta. Is that okay now? Is equal to what? Is equal to theta. Is that okay? So in a bit to express this as in terms of my surface coverage, is that okay? So it follows that I can make this, open this bracket, BP minus BP theta equals to theta. So BP therefore now is equal to theta plus BP theta. Is that okay? So factorizing, you have this. So if that is the case, then your surface coverage therefore, is in form of this. Now, this is what we call equation 9. So, but if you can observe so very well, that's equation 8. So if you observe so very well, you will see that kinetically, all right, and thermodynamically, we have two equivalent terms. Is that okay? So that's a justification, for our Langmuir isotherm. Okay, Langmuir isotherm. So I hope that makes sense to you and you're happy with that. So the next thing to do, so will be for us to see how actually we can apply this. Okay, so we have questions here that actually we're going to make use of. Okay, for the purpose of this video, you permit maybe quickly we can also quickly look at a practical question. Is that okay? So subsequently we can use 3 cases of Langmuir isotherm. It all has to do with derivation as well, and I hope actually we'll be anticipating that as well. So let's quickly move on. Now from this place, so let's move on. So if we have justified Langmuir isotherm, then how do we move? Now recall that theta is equal to V over V infinity, right? So whereby I express V as the volume of the adsorbate. Is that okay? And then V infinity has to do with the volume of the adsorbate, for a complete coverage, on a monolayer. So that's what this is expressed. So you can agree with me that actually we can go here and then just slot in this value into this equation, and then we have this. So we have V over V infinity equals to BP over 1 plus BP. Is that okay? So if that is making sense at all, can we just, just play around with this equation and then do this and say V infinity over V, is the same thing as 1 plus BP, over BP. Hope this doesn't confuse you. All right. So if you are not confused, then, I'm just trying to, by mathematical induction, just bring out, some essential values out of this. So can you just say that from this equation 9, so we can say that B, that is pressure, per volume, okay, is 1 plus Vp, over V infinity. Hope that makes sense, okay? So if that make any sense at all, please look at this very closely. Look at this very closely, okay? So this we are going to be working with. So let's quickly actually simplify this and let it look exactly like what we're looking for. So, all right. From this junction, probably let me write it so properly that you can see. We have this equals to 1 plus Bp over V infinity. I hope you quite understand what we have actually done. Actually, we are driving at something. So now I've been able to express, pressure per volume. Is that okay? So, and then I have all these other terms here represented. But then you will understand that P over V is same thing as 1 over V infinity plus Bp over V infinity. What is this one looking like? Okay? Now, if you remember so very well for your linear equation, you say y is equal to what? Mx plus c. It's not looking like that yet. So just observe. This is P per V. Then we have Bp, V infinity, then plus 1 over V infinity. Take note of that. Now, what does that tell you? Okay? So in this sense, my K, okay, is the my X. So if I plot the graph of this, is that okay? So against the against this, is that okay? Let's do this way. So if I plot the pressure per volume, is that okay? So against pressure, all right, then I have this as my slope. That's its implication. Do you get that so very well? So taking the pressure, plotting it, against the volume, is that okay? So then you can have what we have. So from that, actually, we can determine every other thing we have. Is that okay? So take note of that. So that's what we're going to be playing around with. So mx plus so we plot the graph of, so take note of that. So now take note. So having derived our Langmuir isotherm as this, okay, so this our surface coverage, as a function of the volume, and then the volume, occupied by a modular area for a complete coverage. Then V over V infinity is given as this, so which is quite understood. All right. So in that sense now, the only simple manipulation we just do, because actually we are driving at something. So it's just this, just by simple mathematical induction. So if V infinity is over this, is that okay? So I can bring this P here, okay, to this place. Is that okay? So that actually we're going to have this Y also I bring this one here. But don't forget there is what? There is our constant here. So that is our B. Is that okay? So we have P over V is equal to 1 plus, Bp, B V infinity. So if that is taking the same expression, okay, all right, is written here. So we have this. Is that okay? So if that is taken, then what we then have is, of course, you understand this. So we have this, and then we have this. Is that okay? So it follows that from this expression that we have, B cancel out B. Is that okay? So therefore, by actually rearranging, is that okay? In order for it to look, as a form of a linear equation, so then in that sense now, so the B, automatically here disappears, and then we are left with what? 1 over, B V infinity. So take note of that. Is that okay? So this table is meant for a purpose, but then let's quickly look at our question. But you should note that by plotting the graph of P, okay, over V, that's what we have. That's our Y. That's the ordinate axis. Is that okay? Against P. Is that okay? That's our P, which you have said, that's the horizontal axis now. Then gives, 1 over V infinity. Is that okay? So that's what actually I've just really circled here. Is that okay? So 1 over V infinity. So that is our slope. Okay? Then as the slope, is that okay? That's our, so from that, actually, we can, so 1 over V infinity is our slope. And then, look at that. So 1 over B, V infinity is our intercept. Is that okay? So all of these factors put in place, okay, we can derive our equilibrium constant. Is that okay? and then we can derive V infinity, you know, for a monolayer complete coverage. So now let's take a look at our question. Is that okay? We have a question right before us, okay? The question is states that the data given below are for the adsorption, you know, of CO in charcoal, on charcoal at 273 Kelvin, full stop there. Confirm that they fit the Langmuir isotherm. Is that okay? So actually we are asked to justify, you know, this data, you know, based on Langmuir isotherm and find the constant K, okay, and the volume corresponding to a complete coverage. So take note of that. So in each case, you know, V has been corrected to 180 and 1.080, which is equivalent to 100.325 kilopascal. So the pressure is given in what? In pressure per kilopascal. The volume is given in per cm cube. Then we have all this data given. So this is how your question will look like. Is that okay? So, and then from here, based on the equation that we have here, we can just do a simple manipulation. All right? So on this, and then we are going to do that together. So please follow on very carefully. So first of all, our pressure remains the same. So take note of that. That's P per kilopascal, 13.3. Are you there with me? 26.7. Are you there? 40.0, 53.3, 66.7, then 80.0, and then 93.3. Is that all right? Good. Now, look at the equation, okay? Our ordinate axis there actually is P per V, P per V. So therefore, it follows that we have to derive that. So instead of plotting, instead of this, so then we have, probably, let me write. So we have V, okay. So we have just P, you know, per V, all right? So actually that is, your unit is a kilopascal, you know, per cm cube, you know, your unit matters, okay? So kilopascal per cm cube. All right, so our pressure in kilopascal, that's 13.3. So so this is our working table. Is that okay? Because of those various modifications I've mentioned. So in that sense now, so 13.3 divided by 10.2. So let's leave everything to just two decimal places, you know, to make it easier for ourselves. So in that sense now, so I have 13.3. So you can do it as well. So you divide it by 10.2. 10.2. So you have your result. So that is 1.30. 1.30. So take note of that. So I have 1, you know, 0.30. Take note of that. So hold that. So then the next one is 26.7. 26.7. All right. So divided by 18, you know, 0.6. So you have your answer 1.433. So that's 1.435. So that's 1.44. So just leave it that way. So 1.44. Take note of that. So as if that is not enough, so we have 40.0 divided by 25.5. So 40, you know, 40.0, okay, divided by, you know, 25.5. So you have this. You have 1.57 approximately. 1.57 approximately. All right. So take note of that as well. 1.57. So we move. So 53.3. So 53.3. All right. So divided by 31.5. 31.5. So you have this. You have 1.69 approximately. I've set to two decimal places. 1.69. So take note of that. 66.7 as well. 66, you know, 0.7 divided by 36.9. 36.9. So what do you have? You have 1.81. Take note of that. So that's 1.81 approximately. If you do so, then the next thing is 80. Okay, 0.0, you know, divided by 41.6. All right. So when you do so, so your result is 1.92. You know, 1.92. Take note of that. All right. And the last but not the least on our table, that's 93.3. Right. So divided by 46, 0.1. So here we have 2.02. 2.02. Is that okay? So, sometimes I just like to make things easy for myself. So now having all of this, okay, 13, 26.7, 40.0, 50.53.3, 66.7, 80.0, and 90.0. Of course, you know how to plot graph already. So determine your minimum value here and then your maximum value so as to carefully choose your scale on your graph board, okay? Then, I think I want to make this easier for myself. This is 1.3. Actually, this was ranging between 1 and 2. Is that okay? So I just think of, okay, let me just multiply through by 10. Is that okay? But of course, I have to consider that by the time I'm doing some calculation, calculating my slope and intercept and so on. So you have to be careful. So I say P per V times 10. Is that okay? So this one turns to 13.0, 14.4. Is that okay? 15.7. All right. Then 16.9. Take note of that. Then 18.1. Are you there? Then 19.2. Okay. Then 20.2. So these are my values for plot. So don't forget, plotting the graph of P per V against P, gives 1 over V infinity as your slope, then 1 over B infinity as your intercept. So now on, we are now going to plot our graph. Is that okay? So choosing a suitable scale. So now having this working table, so and their respective values. So 13.3 being the minimum value, for the ordinate axis, and then 19.3 being the maximum value for that. Likewise, for the abscissa axis, we have 13.0 and then 20.2. So these are various things you have. So this one will help us to decide, okay, which scale is appropriate, for you, so that actually the graph can look good, So in that sense now, so let's quickly do that. So looking at this, so we can say that, okay, let's take a kind of interval, 5, 10, 15, 20, and so on. So on the vertical axis, since all we're just having is just between 13.0 and 20.2, and then on the horizontal axis, which actually is extending to 100, so we can actually group them into 10 units each. So fine. So in this case, now I can be using 4 centimeters to represent 5 units, and so on and so forth. So in a case whereby a line here actually will correspond to 0.25, so and then each line here, just a single line actually will correspond to 1. So let's find out. So this is what we have. So in that sense, we have a graph. So ruling that, okay. So we have this. So good. So these are the vertical axis. Is that okay? So, and don't forget, this has been expressed as what? P per volume. And the unit is in kilopascal, per cm cube. So that's what we have. So take note of that. And we have multiplied this by 10. Are you getting my point now? So note it. So on the other side, we have this. So as you can see, all right. So good. So that is happy. So in that sense, on the horizontal axis, we have our P, which is a pressure. Is that okay? That is per kilopascal. Is that right? So let's go. So this is our origin, 0. Okay? So along the vertical axis, we have 5.0, 10.0, 15.0, 20.0. So 20.0, and then we have 25.0. So note that 5, 10, 15, 20, 25. Is that okay? So observe that. So on the horizontal axis, you can simply say 10.0, okay, 10.0, 20.0, 30.0, 40.0, 50.0, 60.0, 70.0, 80.0, 90.0, and 100. Is that okay? Good. Though it's just extended to 93.3. So if all those ones are taken, then we can go ahead and do the plotting. So on the vertical axis, I have 13.0. So where is the equivalence of that? So having told you that each line corresponds to 0.25. So if this one is 10, just count 4 lines, you enter 11. So 1, 2, 3, 4. That is 11. Don't forget, I'm going to 13.0. So 1, 2, 3, 4. That is what? 12.0. Is that okay? 1, 2, 3, 4. That is what? 13.0. So this is exactly where we were going. Note it. Is that okay? But we trace it to the abscissa axis. What do we have? We have 13.3. 13.3. So if each of these lines represents just one unit, so this one will be 11, 12, 13. Is that okay? This will have been 14. But looking at it and then the kind of orientation and then the interval, so we can just approximate, 13.3, 13.0, so no trouble. So you still get your value. So as we have now, so we have 1, 2, 3. So that's our 13. So we trace it, to the to the vertical axis. So and then we have this. So this is our point. So here. So note it. So then you mark. Can you see that very clearly? So good. So that's what we have. Then likewise 14.4. So where does that one belong? 14.4. Let's check it out. 14.4. So if this one is 13, 1, 2, 3, 4. Is that okay? So that's 14. A line here corresponds to 0.25. So if that's 0.25, this one will be 4.25. Is that okay? This one will be 4.5. So somewhere close to that, that's where your point is. So do you understand that? Good. So if that is taken, then we trace it to the horizontal axis. That's 26.7. Very, very close to 27. So where does that one belong? So 27, 21, 22, 23, 24, 25, 26, 27. 27 is somewhere close to 28. So it can be somewhere here. All right? So, and if you agree with me, and then we trace it very well, is that okay? We trace it up, okay? Here we have this. So our point, we fall in somewhere here. Is that okay? So then we can do our plotting, this, and then we plot. Is it all right? Good. So if that is making sense. So we have 15.7. Where does that one fall into? 15.7. Let's check. So this is 15. All right. This is 15.25. Note that. This is 15.5. Is that okay? So actually this one is going to be 15.75. Do you understand? So then if that is okay, then somewhere in between. Is that okay? So that's where my 15.7 will be. Just a difference of 0.005. So in that sense now, so 15.5, so 15.7 will be here. Is that okay? So if that is making any sense at all, then 40.0, where is it? So my 40.0 is here. Is that okay? So I can then trace it. So I have it here. So my point here. So then I mark that. Am I making some sense there? So then, again, we have 53.3 and we have 16.9. So where is 16.9? If this is 15, 1, 2, 3, 4, that is 16. Is that okay? 16.9 is close to 17. So let's go. So that's approximately 17. So if this is 16, 1, 2, 3, 4. So this is my 17. Oh, that's 17. So but then just very close to it and approximately. Then I have 53.3. So let's go. 51, 52, 53. So that's the approximately what I have. So I have 1, 2, 3. Is that okay? So I have my point here. All right. Okay. So how do you mark? Is that making sense? Good. So fine. So then the next one there is 66.7. That's very close to 67. Okay. So where is that? 66. 61, 61, 62, 63, 64, 65, 66, then 67. Is that okay? So somewhere very close to 67. That's where I have my mark. Somewhere there. So if that is making sense at all, then where is 18.1? Oh, that's very clear. So this is 15.0. So 1, 2, 3, 4, 5, Um, so 1, 2, okay. So we are here. So 1, 2, 3, 4. Is that okay? 16. 1, 2, 3, 4. Okay. That is 17. 1, 2, 3, 4. That is what? 18. Am I making any sense to you? All right. So note it again. So let's go by it. That's what this 1, 2, 3, 4. That is 16. 4 lines. 1, 2, 3, 4. That is what? 17. 1, 2, 3, 4. That is 18. So 18 is here. So, and I'm looking for 18.1. Is that okay? So 18.1 is still approximately 18. So we can have our point here. Okay. So if that is making any sense at all, then we can trace the value. So don't forget 1. So 1, 2, 3. Okay. 1, 2, 3, 4. So this is where your 67 is. Okay. So 66, 67, 68, 69. So we have that. So in that sense, now we move. So where does it belong? So we are here. Okay. 1, 2. So this is it. So this 67. All right. So I can mark it here. All right. So that is still making sense anyway. So then we have 19.2. Where is 19.2? That's close to 19.25. So 19.2, where is 19? This is 18. Note that. 1, 2, 3, 4. So this is 19. This is 19.25. So 19.2 will be in between. Is that okay? Okay. Yeah. So if that is making any sense at all, then 80. Where is 8? That one is obvious. So we have 80 here. So then 1, 2, 3, 4. So you have 1, 2, 3, 4. So you have your mark here. Okay. So this is this is your point. Then you mark. Is that all right? So that is what we have. So then again, we have 20.2, okay? And then 93.3. So 93.3 is still roughly 3. So 1, 2, 3. Is that okay? So note that. Then, okay, so let me mark it. 1, 2, 3. So here. So note it. Then we are looking for 20.2. Where's 20.2? If this one is 20, this is 20.25. So 20.2 will be in between. Is that okay? So then we can trace it here, and then we come here, okay? So this is my 93. So this is where both of them actually coincide. So then we have this, and then we have this. So as you can see, this is what? A straight line graph. Is that okay? So actually that tells you actually your what is it called? So P per V, varying, with your P per kilopascal. Is that okay? Though like mark off, for what is it called? For undissociated single species, is that okay? Usually is a curve. So but if you are to plot the graph of your surface coverage, as a function of the pressure, so usually it gives you a curve. Is that okay? But then in a way we have linearized this. Is that okay? And that's why we are making sense as this. So then what can we do in order for us to obtain all the necessary parameters? Recall the questions that we have, so we can then get our line. There's no necessity for line of best fit, as it were, because almost all of them here actually they fell in line. So just make sure that actually your line touch every necessary point here. So that's very important. So that's the key thing. So we have this. All right. Here we go. Okay, good. So this is happy. This is looking good. So here is our line. So from this now, the rest is very easy, as you can see. So we can just determine our slope. So let's look for a convenient triangle. As you know, well, good, right? Then we have this. Correct. Good. Oh, very good. So to make more sense out of this, so can we do this? Let's just locate all our necessary points and then if you trace this one down, okay. So let's call this one, of course, let's call this one P1. Is that okay? So we're going to determine the value. Let's come here and let's locate here. Okay. So looking at this guy here, so we can trace it down. You know, I hope I'm not blocking you. So you have, so can have this. So I don't know whether you're happy with that. So this is P2. So it's equal to some value, which we'll soon find out. Okay? Okay. So, which we'll soon find out. Now let's go. So we'll go here for the next one. So we can trace it to the, see, I'm being careful. But all of these are very important. So good. So I trace it. I have that. Then I come here again. Okay. All right. Good. So I have this. Good. So now, what can we say then? Now, so this corresponds, so the value here corresponds to P over V1. Is that okay? And as you can see, it's a positive slope. I get my point, a positive slope, as it were. So as the value of P per V is increasing, so also is P. So then we have P per V, you know, 2. So those are the two things that we have there. So if that is making any sense at all, so can we now identify? Then another very critical thing we must note, okay, is this point here. Very critical. Okay, that is our high. Is that okay? So this is the intercept. So we need to find out what are those various values. So shall we go? Shall we go? So let's check. Okay. For this, we started by saying, this place, this exactly what? 10.0. 10.0. 10.0. Is that okay? My P2 is what? So if you can check very well, this 88. Is that okay? This 89. That's 88.5. Is that okay? So 181, 82, 83, 84, 85, 86, 87, 88. So this in between 88 and 89. So the boundary value, that's 88, you know, 0.5. All right. So take note of that. Everything here is measured in kilopascal. So then coming here, we have, all right, this corresponds to 20, you know, 20.0, 20.0. So note that. And then here we have, if you check it properly, so let's check. So this is 10.0, 1, 2, 3, 4. That is 11. 1, 2, 3, 4. That is 12. In fact, that 12 actually corresponds to the intercept that we have. So let's quickly note that. So our intercept here is simply 12.0. Very, very critical. So now, if that is 12.0, 1, 2, 3, 4, that is what? That is 13. Is that okay? So in that sense, so this one is simply 12.75. Is that okay? 12.75. Is that okay? In fact, that's 12.73. Very simple. So this place is what? 12.73. 12.73. Let's look at that again. All right? Don't forget each line represents 0.25. So this is my 12. Okay? This is 12.25. This is 12.5. This is 12.75. Is that okay? So plus 0.5 again, that gives what? 12.8. Okay? So that's actually 12.80. So that's 12.80. So we have everything we need now. Okay, so if that is okay, then we move. Okay, so we have that. So we come. Okay, so we can now let's quickly do some few calculations based on our value. So recall this equation where 1 over v infinity represents our slope, and from the graph now we can determine our slope. We are going to show the calculation, and then you'll be happy. So per v, is that okay? So is equal to that is b, all over v infinity. Is that okay? Then plus 1 over v b v infinity. Is that all right? So that is what we have. So excuse me. So this should be p, over. So like I've expressed that, 1 over v infinity represents your slope, by plotting p per v, and then 1 over b v infinity. So this so the whole time here is equivalent to the intercept. So while this one is equivalent to the slope. Is that okay? So we can just quickly briefly calculate our slope. So let's quickly go ahead. So our slope S, okay, so as it is, has to do with change, okay, change in P per V divided by change in P. As you know, that is P per V, all right, 2 minus P per V, 1, okay, divided by P2 minus P1. So if we take that into consideration, but don't forget, like I said earlier, that we have multiplied this value, on the vertical axis by 10, that will make things more easier. So we should not forget to divide it by 10, in order for us to be back at the basic base value. So in that sense now, from the vertical axis here, so our P per V2, is 20.0. So that's 20.0. So take note of that. Then P over V1, so that's 12.80. So that's 12.80. So what is our P2? P2 is represented here as 88.5. 88.5 minus our, what is it called? So P1, as you can see, that's 10.0. So if we evaluate that, okay, so we have that that can be, so you can also evaluate with me. So that's 20.0 minus 12.80. So if we do that together, so the result is 7.2. So got 7.2. So this is 7.2 divided by, so what do we have? So we have 88, 0.5, minus 10.0. Okay, so that gives me, so let's do it together. 88.5, all right, so minus 10.0. So okay, that will give me 78.5. So 78.5, all right. Then we do what? We evaluate that. So that's 7.2, all right. So mine divided by 78.5. So here we have 0.09172. Is that okay? So I just don't bug yourself too much because of these several decimal places. Most often than not, when you do calculation like this, don't just approximate, leave it to at least 4, 3 decimal places and above, uh, in order to avoid, the more you approximate, the more error you generate. So you have to be careful about that. So at your final answer, you can now round it up to anything and then you will be happy. So we have this. So don't forget, this is, don't forget the unit for this. This is in, this our P per V, all right? So this can as well be written. Let me just evaluate this. So this one is kilopascal, okay? per cm cube. Is that okay? That is what we have on that side. And then this one is what? Kilopascal. So that is dot 1 over, kilopascal. So if you do that, so this one will give you in reciprocal volume. So that's 0.09172, per cm cube. So that's what we're going to have. So if that has made any sense at all, so that is our slope. Okay. So that's our slope, which is equivalent to 1 over v infinity. So if you recall for our intercept, so the value of the intercept from there, so and then you relate it with 1 over v infinity, and then you divide by b. Is that okay? So this value, bring it here, divide by b, make b the sort of formula, and then from the value of your height that you obtain there, so you can evaluate your b, which is your constant. So, and I hope you will do that.